Hello students, welcome back to my channel Chemistry with Rahul. So here today I hope you all are doing great. So with reference to our previous lecture, so today we are going to study again. We will revising the part that we have seen. We are basically studying about the electrochemistry. So in this lecture today, we will be covering Faraday's first law and second law, and we will be trying to complete it with the easiest way. And yes, of course, we will be focusing on the examples also. So examples we will be taking at the end of the session, or for the end of the chapter, we can say that. So in this case, so we have already seen that is a Faraday's first law. Like before Faraday's first law, we will be studying about the qualitative aspect. We were studying about the qualitative. We were studying about the qualitative aspects. That is, sorry, not qualitative, quantitative. Qualitative was done actually. So we are studying about the quantitative aspects. Quantitative aspects for electrochemical cell, electrolytic cell. So in this particular thing, we get weight, volume, number of moles. Yes. So we have seen this thing, and before proceeding, we have calculated that is nothing but we required for the charge, that is charge on 1 mole of electron, charge on 1 mole of electron. Yes, charge on 1 mole of electron, that is the most important part. That is how to calculate the charge on 1 mole electron. The calculation part is not mandatory. We can skip this part, but how we got that particular value, that is most important thing. So charge on electron, that is the value. Okay, charge on electron is having certain value. That value is nothing but 1.6 into 10 to the power, that is minus 19 coulomb, this much value. Yes. And when we calculate for charge, like here in 1 mole of electron, in 1 mole, okay, in 1 mole, we get n number, means Na, that is Avogadro number of electrons. Avogadro, that is, it is denoted as Na, that has a value 6.022 into 10 to the power 23. Yes. So to calculate charge on 1 mole of electron, that could be an easier part now. Like what we have to do, we have to just multiply the part, that is 1.6 into 10 to the power minus 19 coulomb into, that is Avogadro part, 6.022 into 10 to the power 23. Okay. So when we solve this part, so after solving this part, we get the value that is around 96, that is 486 coulomb. So we just round it off to 96500 coulomb for our easierness. So this is the value for charge of 1 mole electron, and this same value, charge of 1 mole electron, charge on 1 mole electron, it is referred as a 1 Faraday. It is referred as a 1 Faraday. Charge on 1 mole of electron is referred as a 1 Faraday, and the value of 1 Faraday is equal to 96500 coulombs. Yes, this is it. So with the reference to this value, it will be easier to find out. Now we will again discuss with the Faraday's first law. Okay, Faraday's first law. So Faraday's first law, that basically it works on the basis of the flow of charge and the quantity deposited on electrode. So basically we can say that on any electrode, weight of that particular product weight of that particular product is directly proportional to the directly proportional to the flow of charge, to the flow of charge. Okay, this is the statement for Faraday's first law, and mathematically we can write this as that is a on weight that is represented as W is directly proportional to the flow of charge. Q is a flow of charge, so Q it is denoted as I into T. That is I is the current, T is a for that particular time the current is flowing, and W is the weight over here. Yes. So in this case, to remove the direct proportionality sign, we use Z into Q. Z into Q. This is our constant. This constant is called as a chemical equivalent constant, or electrochemical constant also. Chemical equivalent constant. We refer this term as a chemical equivalent constant also. So Q is charge flow. So to calculate Z, we can write that W that is divided by flow of charge. So Z, that is chemical equivalent constant, it is equal to weight deposited on any electrode is and the flow of charge per flow of charge for the with due respect to the time also. So this could be a definition for this one. So suppose we are taking Q as a 1 coulomb. Q as a 1 coulomb and 1 coulomb for 1 second. Both the term I'm including over here, that is I into T. So Z will be equal to W. Z will be equal to W. So chemical equivalent constant, it is equal to weight which is deposited on electrodes is equal when current is 1 coulomb for 1 second it is flowed. Okay. So we can say that let Q it is done. So suppose we are taking a reaction of molten NaCl. Okay, molten NaCl. In that particular case, Na is giving electron. We can take any half reaction, that doesn't matter. Sorry, Na over here. Na is converted to Na plus, and 1 electron is given out. Yes. So this half reaction we call as half oxidation reaction. We can take reduction also. Sorry, not reduction. Half oxidation reaction. So in this case, to get Na plus 1 mole of Na plus ion, we need 1 electron, 1 mole of electron. So we can write this as a 1 mole of electron. 1 mole of electron, it is equal to 1 mole Na. 1 mole of sodium. 1 mole of electron, it is equal to 1 mole of sodium. And we know that the basic weight, molecular mass of sodium is 23. In 1 mole of electron, it is equal to, we have just calculated this part. So this could be nothing but 96500 coulomb, that is equal to mass of 1 mole of sodium, that is nothing but 23 gram. 23 gram. So therefore, to calculate mass for 1 coulomb could be nothing but 23 divided by 96500, and that too multiplied by 1. This value should be taken over here, and we get the chemical equivalent constant for sodium over here. Okay, this is the part that we can get over here. This is for the sodium we can calculate. Similarly, we can calculate for molten we can calculate for molten MgCl2. Molten MgCl2. Okay, molten MgCl2 we can calculate over here. So Mg could be nothing but here Mg will be giving. Okay, Mg will be converted to give Mg plus 2, and we get over here 2 electron. So for this terminology, we can write over here that is 2 mole of electron. 2 mole electron, that is equal to 1 mole of magnesium. We have the values like here 2 into 96500. Okay, that is equal to 1 mole mg, that is the weight, is equal to 24. So for 1 coulomb we can calculate, this will be 1 coulomb. 1 coulomb will be nothing but 24 divided by this whole value will be shifted over here, 96500 into 2. So this is the value for what? Z of Mg. So for chemical equivalent of magnesium will be also calculated in this part. So here we cannot do this cumbersome process each and every time. What here we wanted, that is to calculate the 1 coulomb part, we can use this factors as a formula. That is, a formula could be nothing but over here we can use a formula. That formula is nothing but, here it will be a molecular weight, okay, or molecular mass or a atomic mass, which is divided by 96500, and this is a 2 electron charge, so we refer this as a n factor. So this is very much important formula, okay, formula we can use to calculate the chemical equivalent constant. So this is the formula that is very much useful to calculate any chemical equivalent constant, or if we want to calculate the n factor also, this could be useful for any any different ways we can use over here. So up to here this is clear. So we got the values. We got the value for Z over here. We got the value of Z. We also have the value of Q. Now we can put this particular value into this particular equation. That is W is equal to. So what we are going to do, we will again write it over here. That is W, it is equal to Z into Q. And we have the value for Z. That is the value of Z over here. That is nothing but, I'm taking as a molecular mass, okay, Q, that is I into T, and whole divided by 96500 into n factor. Okay, so this W, this is the first formula that we can use to calculate the weight, molecular mass, anything whatever we need to calculate. This is the first formula that we can remember, and we can do the changes into this particular formula. That is molecular mass upon n factor. Molecular mass upon n factor, it is nothing but equal to the equivalent weight. It is equal to the equivalent weight also. So this formula can be written in the format of equivalent E into I into T divided by 96500 also. Okay, the first change we can do over here with due respect to this formula. And the second possibility, like given mass, we can do that. One more thing, given mass upon molecular mass, it is nothing but equal to number of moles. We can do this arrangement, like molecular mass could be shifted to denominator to that particular thing. So this could be written as number of mole, it is equal to I into T and whole divided by 96500 into n factor. So this is one more formula that we can use over here. So one more formula from this given formula, that number of mole, it is reciprocal to n factor, to that particular thing. So what we can do over here, that suppose we have n factor for cathode divided by n factor for anode, could be written as, so here this is reciprocal to each other, n factor, this will be like 1 upon n factor of this n factor of cathode divided by 1 upon n factor of anode. So by simplifying this, we will get n factor of anode divided by n factor of cathode. We can write it like this. So the formula could be nothing but Nc upon Na, that is at cathode and anode. Okay, so basically C is nothing but cathode, C is nothing but our cathode, and A is nothing but our anode over here. Okay, so this is the thing that we can use it over here for our further references. Okay, so this is all about the first law of thermodynamics and the formulas which we were requiring for the further process and the further in the chapter. And this is done. So now we will be moving towards the Faraday's second law of electrolysis. That is also very much important. Faraday's second law. Second law. Faraday's second law over here. So to get the justification for this particular thing, we can draw two cells over here. We can draw two cells. Faraday's second law. To understand this, we can use two cells over here. And suppose in this cells we are having electrodes like this. First electrode, second electrode, okay, third electrode, fourth electrode, like this. So let's connect them. Here we get that is negative, then this is our positive charge. This will be a positive, this will be a negative, and simplified we are just connecting this two also. Okay, now in this case, like here, this will be our anode. This will be our anode. And this will be our cathode. And for the internal part, as it will be a positive, this will be a cathode, and this will be a anode. Okay, this is simplified. So for this scenario, what we are keeping current, that is I, that is a constant or a same with reference to time. Okay, with reference to time t, we are keeping this as a same over here. So these two things are same over here, and the cell basically two cells in series, two cell in series over here. Okay, two cells are in series over here. So we can say that like current is same current is flowing for the same time. So with due respect to this particular thing, we can give a statement like here, that is very much important statement, that is for any series connection, series connection of two or more than two cells, that will be nothing but cells. The ratio of their respective weights at electrode, is equal to their equivalent mass ratio. Equivalent mass ratio. So this is the simplified, that here this system basically means that if we are taking this as a B, C and D, so weight, whatever the weight which are at the ratio of weights at W1, WB, WC, WD, it is always equal to the equivalent mass at A, and ratio, it will be in ratio to that particular thing. Okay, so we are going to prove this. This is not important, but the proof is not important, but for our understanding how this has arisen, that is very much important. That okay, so we will be seeing this particular thing. So this is the Faraday's second law. So we can write this in term as W1 upon W2 also, and that is E1 upon E2. This could be also possible for this terminology. Okay, so let's take, suppose we are having, like we know that equivalent weight, it is equal to molecular weight upon n factor. Yes, and W, we have the formula, that is W is equal to, we know that is E into I into T and divided by 96500. Okay, so let's take an example. Like suppose here we are taking is silver nitrate and copper. Let's take a silver nitrate and copper sulfate solution. Let's take this one. Let's take an example of, like, in one we are taking silver nitrate. Okay, so in this, here in this beaker we will be placing two electrodes over here and two electrodes over here also. So in this we are placing AgNO3. We are placing AgNO3, and in this one we are keeping CuSO4. Two solutions over here. Now we are just connecting them, negative, positive, positive. Sorry. This will be like this, negative, positive. So these are connected to each other, and this will be negative and this will be a positive part. So this will be our anode, this will be our cathode, this will be our anode, this will be our cathode. These both are also connected over here. So in this case, what will happen over here? This is our, we are taking this as a copper electrode. We are taking a copper electrode, and this one will be as a silver electrode. Okay, Ag electrode, and Ag in AgNO3 and Cu in CuSO4. So what will happen over here? We will be seeing this one, like in first chamber we will be seeing, and second chamber we will be seeing what exactly going to happen. In first chamber, suppose in first chamber we have taken, like here we have an anode and cathode also. Both the things are there. In anode and cathode is there. So in this scenario, anode, when we talk about anode, so at anode what will happen? Anode is itself a positive thing. So sodium nitrate is there, NO3 minus is there, it will be deposited, H2O is there, and silver is there. These three things are there. And in cathode, similar way, this is our negative part. So Ag plus will be there, water is there, and also Ag is there. Okay, this is for the second section. This is for the second part. So what will be depositing at anode and cathode? That is going to be a very much important aspect for us. So here we have NO3, H2O, and Ag in this case. So here we will be getting Ag. Okay, because the according to electrochemical series, Ag will be there. So Ag will be like here. Ag will be there, like in anode. At anode, this is a positive. So Ag will be giving one electron over here. So this will be like this, and in this case here, so Ag is again there. So Ag is again this Ag plus is going to accept that particular electron, is going to convert to Ag itself. So similar for the copper sulfate, we can see that. So why we are doing this? Why we are doing this? Because at copper and copper, here we will be getting Ag and here we will be getting a Cu. So two things are there for us. So how we can solve this one? That is now important thing. That is, suppose we are taking weight of Ag first and divided by weight of copper over here. So it can be calculated as equivalent weight of Ag. How we have calculated this? We can see that I into T divided by, we have the formula as we have written over here, that this formula is going to, we are going to use over here 96500 to calculate the weights. This will be equivalent weight of copper into I into T divided by 96500. And after cancellation, let's cancel this part. Common part is there. So we get over here equivalent weight of Ag, it is divided by equivalent weight of copper. So this is how this is going to be proved part. So we have proven this part, how this is going to be this formula, and this is actually happens in the cell when we use, like in Faraday's second law, we use a series connection basically, and this is weight is equal to the equivalent weight of that particular metal, whatever weight is deposited on that particular electrode over there. So this is about first part, and the second part, I hope up to here the scenario is clear to you. So here till date we are completed with the electrolytic cell, and then in next session we'll be dealing with the galvanic cell, and after that we'll be moving towards the concentration of solution. That is also most important, and after that we will be dealing with the questions which are based on the upcoming examination. Previous year questions will be there. So we are going to cover all the things which are required for the for this particular chapter, and with the perspective of IIT, JEE, NEET, and mains also. So okay, so I hope so up to here all the things are clear to you. Okay, so if you have any doubt, which is related to this topic or any other topic, you can just ping me. So we'll be able to see what we can do over here. Okay, so till then, keep on studying. Bye bye.